So here in the Pacific Northwest, we're lucky to live close to some spectacular geologic features, including the volcanoes of the Cascades, such as Mount St. Helens, Mount Hood, and Mount Rainier. So these volcanoes belong to the Pacific Ring of Fire, a 40,000-kilometer volcanic belt that stretches around the Pacific. Now, intimately associated with this style of volcanism are economic ore deposits, or high concentrations of elements such as copper, zinc, and gold, all of which are vital for industry and electronics. So if we take a look at my cartoon magma chamber here, because unfortunately I can't get a real photo of a magma chamber, we'll see that it's composed of three phases: a crystalline phase, a molten magma phase, and a volatile phase. So to form an ore deposit, these elements have to partition preferentially amongst these phases. And my research involves a high-pressure and high-temperature experimental study of the evolution of magma chambers, such as we find underneath Cascadian and Andean-type volcanoes. So if we look at my crystal in the top, unfortunately it's a bit washed out, but we'll see that it's compositionally zoned. And much like tree rings record growth episodes in trees, compositional zonation in crystals record information about the magma chamber. So I can use the results of my experiments in combination with analytical techniques to understand and reconstruct the conditions of a magma chamber. Now, all these processes operate deep inside the Earth. So in order to transport these metals to shallower depths where we can exploit them in ore deposits, the fluid phase is the most important part of our magma chamber. So the very crux of my research is to understand the ideal geochemical conditions that lead to the transportation of metals in a volatile phase to shallower depths. Now, this volatile phase is predominantly composed of water, chlorine, sulfur, and other minor components, but importantly, it's very buoyant and upwardly mobile. So in order to understand how a magma chamber leads to an ore deposit, I studied the effects of this volatile phase and the composition that leads to transportation. So my research suggests that it is a complex function of multiple variables that lead to the efficient transportation of these metals to shallower depths. So not only does this have application to exploring and tracing the formation of ore deposits where we can exploit them for economic metals such as lithium, copper, gold, and zinc, but it also has applications to the formation of explosive eruptions, because ultimately it is the upward mobility of this volatile phase that leads to big explosive eruptions like we see at Mount St. Helens, Mount Hood, and Mount Rainier. Now, understanding that explosive eruption and the dynamics of that eruption is vital for understanding hazards associated with living close to a volcano like we are here in the Pacific Northwest. And with that, I think I'm also done very quickly. But there we go. Thank you.